C is G times C over R. G is algebra of a compact connected simple and we had to decide here in G compact and we had a maximum towards T in G and here T is the algebra and we also define TC to be the complexification of T linear T and I also denote by H space I times T. That is a true for the dual of star which is nothing but no C which is same thing as this can be identified with whom over R C over R also the same as T sorry H R C these are the various notations we had, and we have also phi which is set of roots which is same as eigenlinear forms, non-zero, non-trivial eigencharacters on T where it's a joint action on GC. There is a joint action of T on G, but there it acts, all the eigenvalues of elements coming from T are purely imaginary. So you don't have eigenspace there. So only in GC you can get eigenspace. So, and the corresponding eigen characters are what are called the roots, and we need to remark that if alpha is in phi, and here this isomorphism between these two is got by multiplication by I, because on H the various eigencharacters, each eigencharacter defines a linear form on corresponding Lie algebra. You have a character of the torus that gives rise to corresponding tangent map, which gives you a map with Lie algebra of T into complex number. So it's a linear form. So I would have, let me say, characters of T. Usually the notation for the character group of T notation is xt, and this can be xt can be identified as a natural inclusion in whom over R T by R, which is same thing as whom over R H. It's a subset. Each character defines the homomorphism of the Lie algebra of T, which is what I call German T or Gothic T, and we are looking at each one of them defines a homomorphism of T I times R. Okay, you get a linear form, and this is an injection. That's why I can freely think of characters of T as same thing as linear forms of that, because the mapping is injected. So therefore I'm going to assume that phi is a subset of whom R HR. A priori it's subset of this, but this has been identified with this by multiplication by n. Okay, so this is the picture we had. I will also introduce order. It's also denoted H star. Order on H star and phi plus set of positive roots. Phi minus the set of negative roots. This is one of the notation. This is one of the really bad things about the subject. We are going to have lots of notation. In fact, in one of my papers, for the notation I used every letter of the English alphabet, both in capital and lowercase letters. And I also had to every letter in the German alphabet, both capital and lowercase. So the paper will be my paper will therefore be totally unreadable for most people, not for everybody. Fortunately, that happened only with one paper. And also, fortunately, the main theorem of that paper was washed out because somebody proved a better theorem. So, and with a much pleasanter proof. So, nobody need to read my paper. Okay. Phi plus is set of positive roots, and then I define the notion of simple root. Delta is a set of simple roots, and we have this delta, which means this is a set of alpha and phi plus positive root. Alpha cannot be written as a sum of two positive roots. Phi plus with its embedding in H star, phi with its embedding in H star, like the pair H star phi is the root system of G with respect to H. We can make an abstract definition of root system and do many things with them, but I won't go into it. There's the notion of root system independent of Lie-Algebra in the thing we're talking about here. X is the root system, and delta is simple. And last time I stated two lemmas. Lemma 1 is that dimension G alpha is 1. So, priori alpha is phi. The second lemma was that if psi in R and alpha and phi are such that psi alpha is again phi, then psi is plus minus. The only multiple of a root, real multiple of root, which can be a root, is the root itself or the negative of its roots of the root. That's the second lemma I stated. So I proved this lemma, these two lemmas, but for the proof I need something about representations of the simplest simple randomly SL2R. I want to look at the Lie-Algebra SL2. let's see. Let's look at this is usually denoted SL2C is the Lie algebra of 2 cross 2 matrices of trace 0. If two x and y are two matrices of trace 0, then bracket xy is also a matrix of trace 0. Right. X and y can be any two matrices, they don't have to be trace 0, the bracket is always trace 0. In any case, SL2C has the property which is equal to total counted sum. Counted sum. Now, dimension SL2C is of 2 cross 2 matrices of trace 0, so it's a space on a linear form, then you get trace on the 2 cross 2 matrices vanishes, so it's a space of dimension 3. SL2C is a Lie algebra of dimension 3. And it is a very natural basis. You have the vector V, which is 0, 1, 0, 0. The vector F, upper triangular with 1 on the top corner, and there is 1 with 1 in the bottom corner, greater than 0. They are both obviously trace 0, and H, which is 1 minus 1. And we have the following bracket relations: HFE, HE is pi z, HF is minus 2f, and EF is H. These are easy to check. These are 2 cross 2 matrices. Matrix multiplication in general is a clumsy business. And I personally make enormous number of mistakes when I try to multiply matrices in higher rank matrices. But anyway, so this is a easy present business. So what one would like to do is to describe, how the the ultimate aim of my lectures is to classify the representations of all semi-simple Lie algebras, finite dimensional representations. So this is the simplest example of a semi-simple Lie algebra. So if we can do this, we should first be able to do this before we embark on something bigger. It turns out this really holds the key. I won't describe the representations of this. So, yeah. SL2C has up to equivalence 1 and 1 irreducible representation rho on an n-dimensional vector space. So it says here there is a representation rho n of such that the corresponding representation is of dimension n. For every integer n greater than 0 in such a representation, such that given any irreducible representation of dimension q, it is equivalent to one of these rho q precisely if it is dimension q. This is theorem, and moreover, rho n can be taken the representation of SL2 of G vessel to C on the space of homogeneous polynomials of degree n minus 1 in two variables. What do I mean by this? The Lie algebra S2C acts on the two-dimensional vector space, namely C2 acts on C2. And therefore it acts on polynomials on C2. Take any polynomial on C2, the Lie algebra can be made to act on that. You have to be a little careful about this. When I talk of okay, what do I mean by this? So you take the space of polynomials, and of all possible degree, not necessarily homogeneous. Action of so to C on polynomials. Sorry, this is to C on the space of polynomials. How do I get it? You take fx is the polynomial, see, and I want to have to define what rho n of is E itself. So I have to define what rho n of fxy is. Let me write it out as on sigma a pq x power p y power q. On this I have to see how this operates. Q into q very equal to 0 respect to p plus q. For all integers, pq integers. That's what. So rho n e on this is what I have to describe. This I'm writing down the way it works. A p q x power p plus 1 q y power. Basically, what I want to say is, you differentiate this y, you will get q y power q minus 1. But don't give it that, multiply by x. Differentiate y, multiply the result by x. That's what you do to x. You don't do anything. I mean, to x, the degree of x goes up by 1, the degree of y comes down by 1. So if you take a homogeneous polynomial of degree n, say, which p plus q, that be n all the time. If that happens, then you get a homogeneous polynomial the same degree. And therefore, so what about rho n f? Rho n f, the roles are reversed. Sigma p q in n, p plus q. Of course, it's automatic, I don't know what it says. A, P, Q. There are only finitely many terms because it's a polynomial, though written P, Q, and M. A, P, Q, x power P, y power Q becomes. Now we differentiate x and add a multiply by y. So you get A, P, Q, x power P minus 1, 3 times that, times y power Q plus 1. The degree in y goes up, the degree in. What about h? From these two, you can of course calculate h, but it's easy to calculate. So rho n h on A P Q x power P y power Q turns out to be sigma A P Q P plus Q, oh, sorry, 2P minus 2Q x power b by 4. H, rho and H is diagonalizable even on the various symmetric powers, and the eigenvalues look like this. So this is how rho and E is written. One can also think of this on the space of homogeneous polynomials, which is the same thing as the p symmetric power of these two-dimensional vector space. You have SL2 operating in a two-dimensional vector space, which naturally gives rise to the action of SL2 on every symmetric power. The symmetric powers can be identified with homogeneous polynomials. Strictly speaking, the correct way to look at the homogeneous polynomials is the dual of the symmetric power. Not the symmetric power itself, it's dual of the symmetric power. But this is not so important in this case, because what happens is this, we have a representation on SL2 on two-dimensional vector space. This representation happens to be isomorphic to its dual. Whenever you have a representation on a vector space, you will represent on the dual. The dual representation is so if you have a representation rho of SL2C on a vector space G and B, on a vector space B, rho stars are on rho star from SL2C to G and B star is defined as follows. Rho star any x here on linear form alpha by definition is minus of alpha rho x minus transpose. So this is to make sure that the bracket goes to the bracket, because transpose x times y we know is transpose y transpose x. Because of that, you have to get that minus sign.
This action which you have written.
Sorry?
This action which you have written, that comes from differentiating from the group level.
From what?
So how do you write these actions?
I am writing the minus transpose x as a
No, this I am not asking this previously. ONE and ONF.
Oh, the upper one. Basically, what you do is this: you see, if you take the linear case, the natural representation, the dual is the dual of the two-dimensional representation is dual of the it's linear polynomials, which means it's really the dual of C2. And if you examine what's happening here, you will get that.
It's really strange to me because you are simply writing this thing.
Sorry?
You are simply writing this action.
That, no, I'm telling you that you take you have to use the fact that this is what's happening in two-dimensional space. Take linear forms of the two-dimensional space, you will see exactly the formula wrote down. That is the case when p is q equal to 1. In that case, it will exactly the same formula. And then basically it's you extend it when you extend it as if it's what you are doing is a differentiation.
Yeah.
That's what you have already done it for linear polynomials. Then when you want to extend to polynomials of higher degree, you do it as if you are differentiating. In the linear polynomials, so you have already done it, and it is like differentiation, except that when you take x, differentiate but multiply by y. It's like, if you like, you think of it, one is x d by dy, and the other is y d by dx. That's what's happening. On the polynomial level, that's exactly what's happening. One is x d by dy, the other is y d by dx.
The last one.
Sorry?
X. What about x? Rho and x.
The function of two variables, x per p, y per q, we can differentiate with respect to x or y you like, and then multiply by the other variable. That's what you have to do. Okay. So, where was I? Yeah, I am after this theorem. So, the theorem says that you can write down explicitly all the irreducible finite dimensional representations. There is only one up to equivalence in every dimension. And I've told you which one it is. So how does one prove this statement? Okay, now first fix a paradigm representation.
So with this definition of the derivatives,
Sorry?
with this, with this we are identifying the action of.
On polynomials, d by dx makes sense.
But with that, how does the two factor come in?
How? No. When you calculate the.
I just calculate and with that we get that h should come out to be x dou by dou x minus y dou by dou.
No. Calculate the bracket. It's d by dy. Y d by dx. Notice that d by dy into d by dx. There's one term which will cancel out. So to do this, what you get? You get x d by dx. Okay.
X y dou square
X d by dy plus x y dy by dx. Yeah, and you get x d by dx plus y d by dy, and there is this Euler's theorem for homogeneous polynomial.
The second term would be dou square by dou x square.
So d by where d by dx d by dy. Where is the right? Sorry, x y d by dx d by dy. We will reverse and subtract this will get cancelled out.
Yeah.
And then you get x d by dx plus y d by dy. Euler's theorem, which says it gets multiplied by.
No, but then the value of h, that would come out to just p minus q, not 2p minus.
Sorry, it should be.
No, it should be p minus q, not 2p minus 2q.
Well, it's one moment. H is not quite. Maybe something. The point is that there ought to be. No, it's not. It won't be the same for all q. It must be 2p minus 2. Yeah. See, what happens in the. Oh yeah, sorry. That should be missed. You're right. Yes, this should be missed. Yeah. I'm sorry, I got that wrong. Anyway, so how does one prove this then? So proof of theorem. So let rho be a finite dimensional representation on a vector space of dimension vector space V of dimension. Decompose V as a sum V mu direction V mu, where V mu are generalized eigenspaces for H. Now, actually, I'll check a little bit. The point is, SL2C is really the final representation comes under representation of the group SL2C, which in turn comes under representation compact subgroup SU2. The compact, if you take the compact group SU2, its Lie algebra is Q admission matrices 2 cross 2 elimination matrices. And that to complexify, you get matrix reduction. It's a 3-dimensional linear algebra, and what you've got is a SR2C is a complex 3-dimensional algebra. So what happens is this, so the whole thing comes from the compact group. The torus, it breaks up the eigenspaces, and the torus being a compact abelian group, all the eigenvalues are going to get eigencharacters are going to get eigencharacters. So the corresponding eigenvalue of the linear algebra, in fact, the whole thing decomposes into eigenspaces. You don't have to say generalized. So I use that. No, the point is that if you do, you can go without using it, but then it gets a little complicated, which is why I first wrote generalized eigenspace, but I'm going to say simply eigenspaces for the torus, therefore for the linear algebra of the torus, which is T, and therefore for H, which is IT. Okay? So it decomposes into eigenspaces like this. And the corresponding linear forms are real on H. All this we know. But again, these are totally imaginary on the eigenvalues of all elements in T. The linear algebra T are imaginary, and therefore those in eigenvalues of those in H are real. So they are real linear forms. So the one-dimensional situation. So mu are linear forms, real linear forms. On H, which itself so these are, in other words, the elements mu are only let star. On a star order, we have introduced an order on the dual. It's a one-dimensional situation, so order is no big deal. It's your fixed vector H, and simply you say on the value of H, the small h is greater than 0, then you call the element, then you call the linear form positive. Linear form positive is the same thing as the value of the linear form on the single element H is greater than 0. You have to fix the basis, take the basis H. That is, mu is greater than 0 if mu H is greater than 0. You have this order. Definition of order. This is okay. Therefore, it makes sense to talk about the highest of these eigenlayer forms. So what are called weights. It therefore makes sense to talk about the highest weight because we are now talking about linear forms on H. So this representation therefore will have a highest weight. Mu are in weights of let me also let alpha be the linear form H going to alpha of H. In other words, it's the alpha is the root And in the Lie algebra, we have already written down the formulas. He is 2e. That means alpha of h has to be 2. So that's why I call it alpha. Root of is equal to c. And then of course it follows that the u has to be some multiple of alpha. Let me write u has to be equal to some c times alpha by 2 is c. It's a one-dimensional situation, so everything is multiple. I want to fix the root alpha. I say this is it. Now, let R alpha by 2 be highest weight of row. Maybe as R root. And V an eigenvector corresponding to this weight eigenvector of H. Then notice first, then one has E of V is like it's an eigenvector with eigenvalue, eigenlinear form. We will eigenvector correspond to this weight, which at this point I still call the whole thing lambda, so that right. Otherwise, I'll have to keep writing R row alphabet all the time. So, if VP is an eigenvector with the eigenlinear form, lambda plus alpha. This is easy to check. What do you have to do? You have to see what happens to H on EV, which is HE minus EH V plus EHV. What is this? HE minus EH we know is bracket of EH is 2 of V plus EHV. HV we already know is lambda V, so this becomes 2 lambda. In other words, something but lambda plus 2 EV, which shows that the corresponding eigenvalues. I mean, yeah, this should have written there lambda H. And this is obviously lambda H plus 2. Is nothing but lambda plus alpha of H. But then that shows that EV is an eigenvector with eigenvalue lambda plus alpha H. But when we assume that lambda is highest possible weight, this becomes higher. It becomes lambda H plus 2 the value at H. So, which is a contradiction, unless of course this EV is 0. All this implies that EV is 0. EV is an eigenvector with eigenvalue bigger than the original eigenvalue lambda. That's impossible because the original lambda was assumed to be the highest of all the values possible. I don't see approval with many faces. Think of it, it's a simple matter, and I don't want to spend too much time on it. See what happened. I start with the vector v corresponding to eigenlinear form, which is highest among all the eigenlinear forms, in all the weights. Apply E to that vector. This is the vector with the highest possible eigenvalue. Apply E to that vector. I made this calculation. I find I get the new eigenvalue is lambda plus alpha h, which is lambda h plus 2. So it's more bigger than lambda h. The eigenvalue of h is that bigger than lambda h, which in our definition of order is impossible, because already lambda is highest, and that proves that vector has, there is no vector that has eigenvalue, which means EV has to be 0. There is no other choice. EV has to be 0. So that is the important conclusion we come to start the highest. Then what happens? Once you have that, we are after all working with an irreducible representation. So this vector, if you keep applying elements of Lie algebra and take the span after doing it repeatedly, will ultimately will be the whole space. So let us see how to go about it. Apply F now. We know that EB is 0, and let's see what happens if you apply F. You have the vector B, EB equals 0. And let me write, maybe I call B itself V0. And then set V1 to be equal to F V0, V2 equal to F of V1, so on, Vi minus. I define V1, V2, Vi like this. Observe F itself, notice that H of Fvi, so H of Vi is going to be equal to lambda H minus I here. Because F is the eigenvector corresponding to -2 for H. So if you keep applying H, it's the first time of the H increases by 1 and so on, finally it decreases by 2 and then finally 2i. Sorry?
So you are getting from lambda h minus 2.
2i, yeah,
Remove this I.
we.
I lambda h minus 2.
No, lambda h minus 2i, not I.
Minus 2.
That's correct. I do make some mistakes like that, but this time it's short. About it. HVI becomes lambda h minus 2i. And there's an interesting thing that happens. So I went about doing all this at some point, and in particular, they all become linearly independent. If they're non-zero, they're going to be really independent because eigenvalues are not different. There are different eigenspaces. And since vector space is finite dimensional, at some point, F will have to vanish. So F VR equals 0. In fact, if we assume the vector space is of dimension n, so it has to FBR is 0 if R is greater than n. In fact, R greater than n minus 1 because start with 0, FBR becomes 0. Keep on doing it. Beyond the change, FBR we are going to 0. If once r is greater than n minus 1. So you can stop at n minus 1, no further limits. So, Fv naught, Fv1, Fvr. It may become 0 even earlier, a priori. We don't know when it becomes 0.
But then it's eigenvalue of x has to be real, right?
Sorry?
Eigenvalue of x has to be real, right?
Yeah.
Now x minus 2y, how it is real?
I is not imaginary.
I think.
Square root of minus 1.
Sorry.
I.
Sorry.
I remember a very interesting story. There was a visiting lecturer, French lecturer, to the Tata Institute, a colloquium, and he did the same mistake. He used I for square root of minus 1 and also for integer, random integer. At some point, one of the people in the audience, a senior professor, mathematician who lectures blew up, the great French mathematician. And they said, what is that I? Is it square root of can't be square root of minus 1, can it be? But that is stupid. To ask that question, what do I say? Anyway, well, sorry. I have not offended you. Anyway, yes. So you keep doing this, and at some point it becomes 0. Maybe it could become 0 even before n minus 1. We don't know where it becomes 0. We know as we want the linear independent, go beyond that point it becomes 0. That's simply true. Now, yeah, this is given. Now, what I want to do is the following. Let us look at what happens to E of Vi. I want to say it becomes something like some constant Ci times Vi minus 1. We'll see, inductively you can determine what the constant is. So, let's see what happens to this is a claim for some Ci. So, suppose you proved it up to some stage I. Let's see what happens to E Vi plus 1. This is equal to E of Vi by definition. Vi plus 1 by definition F Vi. And this equals, we know, by induction hypothesis, we know that, so write this as EF V minus FV on Vi plus FVBI. In which way? EFVI, EVI plus 1 ZFVI, yeah, plus FVBI. Sorry, no, plus FVBI. Okay, we know that this is after all HVI plus EVI. By induction hypothesis, I know that EVI is Ci minus 1 or Ci of Vi minus 1. Okay, and if I apply F by definition, FVI minus 1 is FVI, so this is HVI plus Ci F Ci of FVI minus 1, which is Vi. And this HVI we know is I wrote it down somewhere. Where was it? This lambda h minus 2i plus ci, which gives you that ci plus, this is therefore to some ci plus 1. Vi, which implies where ci plus 1 equals this right hand side ci plus lambda h minus 2i. Vi. This enables you to inductively calculate this ci. Ci plus 1 is expressed in terms of ci and lambda h. No problem. We can able to calculate this one. And the start of the induction is when you want to calculate V1. Sorry, but calculate E V1, which is nothing but EF V0, which I write as EF minus FV V0 plus FP V0, but this is 0, and so lambda HF V0, which removes lambda H. So the start of the induction is C0, or whatever C1, C1 is lambda H, and then you have the inductive formula. Essentially, you are starting with lambda H and subtracting the sum of arithmetic proportion terms more and more. And the upshot I want to say is the following. Turns out that lambda H the dimension of the representation is n. It turns out lambda H minus n plus 1 2n plus 1 lambda h minus 2n plus 1. No, sorry, lambda h minus 2i is it? Confused. Is 0. In other words, all this implies to go through the inductive procedure, make construction. See, the point is that when you reach, hold on, I'm not saying it right. Keep doing this. So the final outcome of this report says the following: lambda h equals n plus 1, where n is the dimension, then lambda h happens to be n plus 1. Because when you go down, at some point you are going to get 0. At that point you add up everything, what you get. And then it turns out that lambda h becomes equal to n plus 1. When you do the thing to make, if you want to make it 0, you have to go all the way to, you will see that if you make the inductive construction and you want to arrive this at a vector b, which is, you want to arrive at a vector b r, where area r is 0, r is necessarily n. It turns out. It's a simple calculation. So,
It should be a plus 1 by 2.
sorry?
Should it be a plus 1 by 2?
No, h takes the eigenvalue taken by h is always an integer. 2 doesn't figure. When you take n equal to 3, the adjoint representation, you get 4. Lambda h, sorry, lambda h, maybe you're right, one more, I think. It's the eigenvalue of h in the adjoint representation is 2. So in the natural representation it is 1. So its point is this lambda h. Yeah, it's then minus 1 or 10 plus 1. If n is a dimension, you get lambda h equal to n minus 1. So for example, the adjoint representation, three-dimensional representation, the real algebra, plug in 3 here, lambda h will be 2, which is alpha h, which is what you want. And the natural representation, the eigenvalues will be h star 1 and minus 1. So and now, if you, so you know how all this tells you how E, F and V operate, E, F and H operate on the space. So this tells you how what the representation looks like. Now look at the space homogeneous polynomials. On this, the homogeneous polynomials have the following. So homogeneous polynomial of degree n has dimension n plus 1. X power p, y power q, p can be 0 or q can be 0. So p plus q equal to n. So start with p equals 0, then it goes up to 1, so I have to get n plus 1. At the, let's say y becomes, the power of y becomes 0. So fix our homogeneous polynomial degree n has dimension n plus 1. And where is the representation? You choose this polynomial as x power p, y power q. As p and q vary, that's how you get a basis for the space of all homogeneous polynomials. And that basis, you have to modify this basis a little bit to get, you suitably multiply. P plus q is always n. You multiply this by some new p, depending on p, and therefore q, because p plus q is always n. You look at this collection, new p suitable rational number. To do that, you get the same basis what I got here. These are all eigenspaces. So they are all good. We start with apply this term, take this term xp or xn, apply e, you will get nx power n minus 1 y. And then apply e again, you are going to get n into n minus 1 x power n minus 2 y and so on. So you get this basis element except for the scalar, different scalar. So if you choose this, modify this, each of these by a suitable scalar, then you will get back to the same basis as here. I mean, I got this like vector v0, this will be v1. To be consistent with this is what you do. Call this v1, call this v2, which means you original basis are modified by multiplication by division. To do that, you will get back this relationship. So the space of homogeneous polynomials of degree n is the same as this n-dimensional. The degree n plus n minus 1 is the same as this space we will construct now. That shows the degree reducible representation is one of these. Okay, now we got it. I'll take 5 more minutes because my aim was to prove the lemma and I was going nowhere. The sum of dr plus alpha plus GC is GC and the alpha here plus plus EC, what I had. Okay, now what I do is the following: fix some alpha in phi, and let alpha dot be the corresponding linear form on T. I look at kernel alpha dot, which I will call TC is subscript alpha. It's a linear form. And notice it's also the kernel of any multiple of alpha. It's a linear form, so it's a linear subspace, 4-dimensional subspace. And this is equal to T C psi alpha for every psi not equal to 0. Maybe I should put alpha dot is what I called it, so T psi alpha. Alpha dot is same as psi of alpha, psi times alpha dot. The kernel is same. Kernel of alpha dot is kernel of psi times alpha dot. For psi not equals. So I was looking for multiples of alpha which can be roots. What I want to prove is only multiples of possible are plus minus alpha. That's what I want to prove. So what do I do for this? The idea is this. First, I prove the following statement: fix an element, fix E alpha in E alpha. Fix a vector E alpha in C alpha. And we see the killing form is non-degenerate. I noted the killing form like this, and it is not degenerate, which means, and I told you last time, that it pairs G alpha and G minus alpha non-degenerate. For given any element x in G alpha, there is an element y in G minus alpha such that xy is not 0. Or if you like, xy equal to 1. Fix E alpha. So there exists E minus alpha, G C minus alpha such that E alpha E minus alpha with respect to killing form is 1. If I choose such a E alpha E minus alpha, what happens is this. Look at the element E alpha E minus alpha, bracket. This necessarily belongs to its physics. When I take the bracket in these two, the eigenspace corresponds to 0 because alpha minus alpha is 0, and so it's going to belong to these two. And let's see what happens to E alpha E minus alpha in the product with any h. This equals E minus alpha bracket E alpha h. This is the comes out of the fact that the killing form is invariant under the adjoint action. You have in general x of sorry, minus this is a very easy thing to check. Because of this property, you get this, and then what happens? This bracket is nothing but this is minus E minus alpha. Alpha h times G alpha with the minus sign because of interchange also with constant this. So you find that this inner product is nothing but E alpha E minus alpha is 1, so this is nothing but alpha h. In other words, this element E alpha E minus alpha must be equal to what I called H alpha last time. This is a unique element that H alpha H is alpha H. So, all this goes on to show. So, what happens is E alpha E minus alpha is H alpha. H alpha E alpha is alpha H alpha E alpha. And E alpha H alpha E minus alpha.
Are you so that it's alpha belongs to PC?
Sorry?
So how are you saying that it's alpha belongs to PC from that line?
I calculated it. I've shown that H alpha, by definition of H alpha is alpha H. I've calculated this in the product.
Okay, non-linear.
Okay. H alpha E alpha is alpha H. H alpha E minus alpha is E minus alpha. Minus E. Minus alpha H alpha E minus alpha. Actually, you can, by suitably multiplying the killing form, instead of using the killing form, use suitable multiple. So, alpha H alpha becomes equal to 2. Use a multiple alpha H alpha and get equal to 2. To do that, you find that. So, what is by? If you could say modify E alpha by a scalar, get E alpha E minus alpha H alpha H alpha E alpha equal to twice E alpha and H alpha E minus alpha equal to minus 2E. But this is same thing as our triple E H F, the basis which chose for SL2, and the bracket relations are the same. So what happens is that this Lie algebra generated by this is the 3 subalgebra because they stay in the brackets of all 3 elements. And so we find this Lie algebra C alpha plus C minus alpha plus CH alpha is transformation of it to CE plus CF plus CH, which is by definition surface. So inside the subalgebra which I defined, which I called, I did not define it as well, I'll come to that. I had this element H alpha. It actually happens to be contained in a 3-dimensional algebra, isomorphic SL2C. What I do now is to look at the centralizer of the element centralizer with Z of forget what I called it. Where was it?
Raghunathan, would you like to finish?
The kernel of alpha they called PC alpha. I looked at the kernel of alpha, which is called PC alpha, and look at its centralizer. This contains G psi alpha for every psi in R with psi alpha level. So in particular it contains the subalgebra CE alpha plus CE minus alpha plus HR, which is isomorphic to
Raghunathan, you may want to continue.
Sorry?
You may want to continue next time because there is.
Yeah, I think
another lecture.
One more minute, because it's a little abrupt if I stop here. I just want to make two comments. You look at the centralized of this, and then I can form the Lie algebra 3p alpha c modulo P alpha c. If I do that, I get a semi-simple algebra of rank 1. And inside the algebra, this SR2 is contained. So this is, say, some G prime, which contains this SR2. Now, this G prime is therefore can be considered as you have the adjoint representation SR2 on this G prime. So this can be considered as a representation of SR2. And therefore, we know how it has to break up into irreducible representations, etc., etc. And if you do that, you examine that, you find the fact that the eigenspace corresponding to 0 of H alpha is one-dimensional, forces the representation to be three-dimensional. There is a three-dimensional representation. The Lie algebra itself represents a three-dimensional thing, and if there is more, there will be more higher dimension, 0 eigenspace, which is impossible. So, using the representation theory of SR2, you conclude that this eigenspace is one-dimensional and no multiple of alpha can be a root unless it's plus or minus alpha. Both lemmas come out immediately. Okay, I'm going to stop there. I'm sorry I rushed these two lemmas somewhat, but I couldn't really help it.
For minutes.
We start